All right, so with that, let me officially announce the start of the conference on 90 years of quantum mechanics. So first, I'd like to once again welcome Professor Phua Kok Koo on stage to chair the first session. Let's give Professor Phua once again a big round of applause.
The next speaker is Professor Hooft. I don't think I need to introduce Professor Hooft anymore. Professor Hooft.
Yeah. Sure. I think we can connect to you. This is. Oh. Yeah. This side. Sorry.
You need the microphone.
Okay.
Thank you very much. So it's a real pleasure for me to be here and to start with the very first talk about quantum mechanics. Originally, I wanted to talk only about black holes in quantum mechanics because I think their role is absolutely crucial for understanding a lot of things. But then I was persuaded I should also talk about my own private way of understanding what quantum mechanics really means. And the reason why I hesitated to talk about that here right away was I thought I would only get very little attention and very few people would accept what I'm going to say. It's a little bit like the story of the emperor wearing no clothes. That is to say, there is no fundamental difference between classical mechanics and quantum mechanics. That's roughly the story of my way of interpreting quantum mechanics. There must be a classical theory lying behind it. Of course, saying that doesn't solve all the problems that we have with understanding quantum mechanics this way, because even already in the beginning of the 20th century, such ideas were fundamentally rejected. But I want to show to you basically why I think one should think nevertheless of a kind of cogwheel explanation of quantum mechanics. The whole world is a computing machine, very classical in a sense, and yet we will see quantum mechanical behavior. I'll try to explain that therefore in this talk, and so my talk now consists of 4 chapters. The third of this is really, or the third and the fourth perhaps, is the real thing I wanted to talk about. I'll shorten them a little bit and I'll give you a lengthy introduction to what I call the cellular automaton interpretation of quantum mechanics. Basically saying there is no quantum mechanics. Sorry folks, you got it all wrong. Well, that's of course too simple. Quantum mechanics is a very, very essential element in our understanding of physics. Without quantum mechanics, the entire 20th century physics wouldn't have been what it is now. But I'd like to explain to you, first of all, my attitude at this subject. So suppose we had a universe consisting of cogwheels. And I'll tell you what the catch is later and why things are as complicated as they look today. The simplest model, perhaps too simple for very good reasons, but let's go along for a while. Suppose that we had a deterministic system of cogwheels, and the prototype model of that is an absurdly simple universe, a universe consisting just of n states. These n states are classical, and the laws are that state number 1 evolves to state number 2, state number 2 evolves to state number 3, and so on until we reach state number n, and that goes back to 1. That's just a periodic universe. Okay, it's too simple. Our universe is not periodic, but if you look at very tiny subsectors of our universe, they have many periodic features in them, as you know. Everything that oscillates basically periodically. So let's assume the universe consists of periodic systems, but then they are coupled and they make the whole thing much more complicated. But still, as soon as you look at the finite section of the universe, it will have a finite Poincare recursion time, so it will be periodic in the very end. Let's stick to that for a moment. Then the elementary idea is, and of course people thought of this in the early 20th century already, that all you do is that these n states that the universe can be in can all be attached to a Hilbert space, saying that I have an n-dimensional basis of Hilbert space. And that basis then obeys the same commutation rule, the same evolution rule as the classical system, and that can be very easily expressed in terms of a unitary evolution operator. The evolution operator just contains zeros and ones. It so its first column contains 0, then a 1, and then a 0 downstairs, and so on and so forth. So this evolution operator reflects the classical motion of this system. And then from that point on, you use mathematics. Now, mathematicians have learned to use matrices in permutation operators long ago. When you study Lie group theory or discrete group theory, then you find that it is very fruitful to attach matrices to the permutation operators. A permutation operator doesn't know anything about Hilbert space, but you can attach Hilbert space to it, or vector space if it's finite dimensional, and then say I'm going to use matrices to describe a permutator. Very, very useful mathematically, and so the basis idea about the cellular automaton interpretation is that basically what quantum mechanics is about is just this, that we attach to a classical system, we attach matrices to explain, to say something useful about its evolution. It becomes so tremendously useful that today we only know these matrices, but we forgot where, or we couldn't imagine where they actually come from. So the big problem today is find this underlying classical system. And once you say this, it's easy mathematically to write any operator which is unitary as the exponent of a Hermitian operator. To find that Hermitian operator is relatively easy, but not unique. There are many Hermitian operators H, which when you exponentiate give you the same evolution operator. And the reason is that the identities should only hold at integer time steps. So a classical system, like a cogwheel, just clicks from one time to the next. So it has a fundamental time unit. And that makes things a little bit difficult and mathematically non-unique. But let's continue from there. Because the parameter time, it will be very dense in a universe, I'm typically imagining that the fundamental time unit is the Planck time, 10 to the minus 44 seconds, which is tremendously short. So if at integer multiples of the Planck time, the classical model just agrees with the quantum model, then we can say for sure that this is a very accurate model that tells you what happens in nature. So I make a distinction between the cellular automaton theory and the cellular automaton interpretation. The theory is that indeed such a classical system of cogwheels exists. This is a little bit of a blasphemy in this company because we are all used to thinking quantum mechanics is something totally different from classical mechanics and totally unique. But this is the statement that yet there exists some classical system of which the unitary matrices that we work with today represent how they evolve. So in a sense, quantum mechanics would just disappear in a remarkable way, and it does, and I'll try to explain it to you. So there are very important remarks to be made here. What about superposition? So of course we are used to thinking that now we have two of these ontological states the universe can be in, but you can consider superposition between these ontological states. And the remarkable thing about working with matrices and what makes these matrices so powerful is that if you look at the superposition of two states, you can say that that evolves by the same Schrödinger equation. And if you do that, then it becomes immediately evident from mathematics that if you take the absolute square of whatever you call that, then get a wave function, you could call it. If you take the absolute squares, they can be interpreted as probabilities, because then the probabilities will evolve with the same classical law. So indeed you have a working theory of classical probabilities. If you just take this wave function, you postulate that its component squares are probabilities, and then you get a logical description of probabilities as it should be in nature. They evolve correctly as probabilities do. If you have a deterministic system, but it is controlled, but since we don't know the exact state the universe is in, we have a probability distribution the universe is in. Once you have that, that probability distribution will also evolve as if psi indeed is a quantum wave function. So at this level, quantum mechanical and classical just coincide. There is no fundamental difference. So what about the Born probability? Now, superficially, when you look at quantum mechanics, there's a huge difference between classical theory and quantum mechanical theory. In a classical theory, the probabilities are induced in any measurements because of two reasons. One is you don't know the laws of physics with infinite accuracy. Suppose you did know the laws of physics with infinite accuracy, then you could still compute how a system evolves, but what you don't know is the initial state. How can we know the initial state of an experiment with infinite accuracy? Of course, we don't. When you do an experiment, all the atoms in your apparatus are in some positions. But when you switch it on, you don't know in which positions all those atoms are. So you have to use probability distributions. Probability distributions of the initial state, which then, of course, work their way through the whole system until in the final states, again, you have a probability distribution. If you do a scattering experiment with two particles, but you don't know exactly the orbits of these particles, only a probabilistic distribution of these orbits, then you don't know how they will scatter. That is true in classical theory. In quantum theory, it's also true. At first sight, it looks as if in quantum theory, the probabilities are due to a very, very different mechanism, the Born rule. I claim that the Born rule now follows completely naturally if you apply this mathematical method of attaching matrices to classical operators. So I've all written this down, and you can read it in the literature. I'll now just summarize what you then find. So I'll make a distinction between the ontological basis, which is the basis in which the universe just is in its cogwheel states, and the standard model basis. So we are using the standard model, which is controlled by fundamental quantum mechanics, which evolves using a Schrödinger equation. The claim is there is a mapping. The mapping will be very complicated, and I think the real problem of what I'm talking about is how this mapping can be as complicated as it is. In particular, it involves entanglement. So the pure states of the universe can be in will map onto entangled states when you reach the level of the standard model. And one big mystery is, where does this entanglement come from? That essentially will be the problem of quantum mechanics. So I'm not saying I'm solving that right on the spot here. No, it's not that easy, of course. So we have to understand where entanglement comes from. And entanglement means that the initial state of an experiment already is an entangled state of what I call the ontological states. And the reason why this entanglement occurs is apparently that at the classical level, there is a gigantic amount of very strange correlations between the initial states. So, of course, this is handled in a Bell-like experiment, that if you do any experiment that John Bell has beautifully described, you find how strange this is. You find that the only way to explain Bell's experiment in terms of cogwheels, most people say it's impossible, But then you forget something, that also the actions of Bob and Alice themselves are controlled by the same equations. Bob and Alice are part of the universe, also controlled by cogwheels, and that deprives them of free will. Now, this argument has been repeated many, many times, and I shouldn't repeat it all here, that that's not the complete solution of why Bell's inequalities are violated by quantum mechanics. So now, of course, I have to answer a very important question. How can it possibly be that you get these violations of the Bell inequalities? If you argue classically, you get more constraints in your predictions than what you find not only in quantum mechanics but also in experiments. So there is a problem. And that problem now lies in the initial states. So, as I said, the wave function reflects probabilities, but the wave function is extremely complicated. Apparently, our difficulty that we have today in interpreting quantum mechanics is why is this initial state so tremendously correlated in a very complicated way. But actually, although now I have moved all the difficulties that we have in quantum mechanics in the question of correlation functions, there is no fundamental contradiction, and this is what I would like to emphasize. It's complicated, it's difficult to understand, it's counterintuitive, all that, but not a fundamental contradiction. And that is because indeed Bob and Alice in their settings are very strongly correlated with what these polarized photons are doing when an atom emits 2 photons in a total spin 0 state, 2 entangled photons. The entangled photons are only entangled because apparently the initial state already is very much correlated. Now, let me see. Oh yes, this is a kind of super determinism, and the question is this super determinism rejectable? And I think not. It is strange, it's counterintuitive, but it's not a fundamental contradiction. It's just saying that if you make a classical model of Bob and Alice watching at 2 entangled photons, is that the photons can, yes, they can, each photon separately can be in different polarizations, but then the correlation with the photon going to Alice and the photon going to Bob, the strange thing is these photons are very highly correlated. They're described by an entangled wave function. But if you look at my original description of probabilities, the notion of entanglement doesn't enter. So the wave functions can be chosen as complicated as you want. And that includes entangled wave functions. So in principle, there is no contradiction. And that is what I would like to emphasize here. The counterfactual thing is, yes, the difficult thing is that if you look at these photons, then the decision Bob will make to choose the orientation of his polarizer, the decision Alice will make to choose her polarization of the polarizer, is correlated to the polarizations of the photons that they are looking at. This is very strange, but again, not a fundamental contradiction. You can say that if Alice would change her mind the last second, by whatever you could call free will, then that would be a counterfactual change if you don't at the same time change those photons. Counterfactual in the sense that Alice is not allowed to make a superposition of 2 of her initial choices that she could have made because these superpositions are not ontological. The universe never is in a superimposed state of these classical cogwheels. It always is in a pure state. So if it is in a pure state in the very distant past, it will be in the pure state in a single state in the very distant future. So there's an ontological conservation law. And I think the problem with the interpretation of Bell's experiment is that if you do it not quite right, you'll find that Alice or Bob or both are making counterfactual choices of their polarizers. And that's not allowed. Whatever they do, their actions are linked by, you could call it superdeterminism, to how these photons are polarized. And I find there's no fundamental contradiction in that, but I do realize that the burden of proof is in my hands, proof that this whole picture works. And the only proof will be find a way to rederive the standard model from a classical underlying theory. That turns out to be extremely difficult, not very surprisingly, and has not been solved. So as long as that's not solved, you might sit here just not believing me, and I can't convince you. So this is a very important assignment that I'm having, and I realize this. So I now want to explain to you that how important gravity is in this argument. Without gravity, the standard model could in principle be exactly true theory. Without gravity, we wouldn't have the difficulties at the Planck scale. There would somehow be some sort of asymptotically free theory at the Planck scale, and we could all go and do business with that quantum theory. It would be a fundamental theory of quantum mechanics. That theory will be very, very difficult to realize in terms of cogwheels. And so, but here we are, and we know that at the Planck scale, the gravitational forces become inseparable from the rest, and gravity is going to dominate. And gravity is a complicated theory. It's going to change everything that I said. I'll try to explain one thing. In my introduction to the cellular automaton interpretation, I forgot one thing, which is that a classical system doesn't have to be time reversible. Time reversible means that if you have some state now, you can derive what the state was in the past. In quantum mechanics, you can do that. The Schrödinger equation can be extrapolated forward in time exactly as easily as backwards in time. So in quantum mechanics, there is in principle time reversibility. In fact, quantum field theory has CPT invariance, which says that if you invert the time, all you have to do is also replace the particles with antiparticles and flip parity of the space-like description, and that's all. Then you can go backwards in time. In classical theories, that's not necessary. What you see here on the graph is a classical universe, a little bit more complicated than the prototype I had before. Again, this thing is much too simple. This is a universe which has many Poincare cycles. The arrows show how these different states evolve, and the green states, so-called gardens of Eden, they have no past. The universe can never be in a state which has no past. That sounds ridiculous. But, okay, most states have no past here, but they evolve into, finally, they end up in cycles. So in this theory, if you just switch on the evolution operator and just let things go, this you could put in a computer, then you always end up in cycles. And if you look carefully, you can see what these cycles are. There are short cycles and long cycles, and when you start at some point, you don't know yet in which cycle you are. This is fundamentally more complicated than just a simple periodic universe. But you could say, well, wait a minute, this is not more complicated. I just cut off all these crazy branches which in the past end with on the green Garden of Eden, because the universe can never be in there. After a few steps, the universe will be in one of its Poincare cycles. Well, this is not quite true for the real universe. The real universe is far too complicated ever to end into a Poincare cycle. These Poincare cycles last tremendously long. So, and the universe is also expanding. So here you see that gravity changes this picture already. It makes the universe expand. The universe will never be in a Poincare cycle. So the real world is, of course, much more complicated than this. But if I look at a small subsection of the universe, it might look something like this. And now you would say, aha, now I got you this you cannot describe using quantum mechanics. Well, it's not quite as simple. You can do something. And that is introduce information equivalence classes. So if you, and that I'll do by looking at little subsets in this thing. If you look at these two subsets, take any one of them, say the top left, you see that all these states, after one time step in the evolution operator, all these states enter into the same state, this one ball that they all point to. And also the subset downstairs are a set of states which after a few steps, one step or many steps, they evolve into the same state. And from that moment on, we will never know where we started from. So the information in all these sets which are encircled by in a single blob, the information is the same. These different states are fundamentally indistinguishable. So what you do to turn this into ordinary quantum mechanics, is that you say that it's not a single state to which I have to attach an element of Hilbert space, but an equivalence class. So the two brown things are all equivalence classes. They are the new blobs. They are the new basis elements of my Hilbert space. And now it is time reversible. So now the unitary operator connects equivalence classes to equivalence classes. That you can do forward as easily as backward. And so now you have again a unitary operator. You can exponentiate that by saying it's the exponent of a Hamiltonian, and on you go, you do quantum mechanics. The price you pay for this is that this might be non-local. These elements which are sitting in the same blob might non-locally be very different from each other. In fact, they'll cause very complicated correlation functions, and there we are. What we really want is entanglement between these correlation functions, and that's, I think, what this model might easily give you. So now the forward description, the description forward in time is very different from description backwards in time. But quantum mechanically, the model you get will again be time reversible. So the theory will resume unitarity, and the elements of the ontological states of the Hilbert space are now the equivalence classes. Question. This is very much like equivalence classes we already have in physics. We heard Professor Young talk here. He is one of the founders of gauge theory, in particular non-abelian gauge theories. Gauge theories also have equivalence classes. They're called gauge equivalence classes. They are the orbits, mathematically speaking. And if you are in two different members of the same gauge equivalence class, physically you cannot distinguish in which they are. Now there's an interesting suggestion. Maybe the gauge equivalence classes and the information equivalence classes, maybe that's the same thing. Maybe the fundamental underlying theory, if you start with a gauge, in two stages a gauge equivalent, you don't know, maybe they will merge to the same state in the future, maybe it will be different, you can't tell. Suppose that were the case, well, it would make a lot of sense. It would explain that nature is a little bit more complicated than just a time reversible cogwheel. No, these are time non-reversible cogwheels, and they give rise to gauge equivalence classes. Let's suspect that for a moment. Isn't that nice? And I would say, yes, that is very nice, that is very suggestive. When we try to construct a classical underlying theory of the standard model, maybe we have to introduce gauge invariance this way, by saying different elements of the gauge classes are all going to evolve at one stage or another into the same element in the future. And that's why we have gauge theories in the first place. In particular, this holds for local gauge theories, although for global symmetries you could also perhaps say something like this. So now what about gravitation? Gravitation is also a local gauge theory. It has the transformations of the general coordinate frame that you're using, the general transformations of that, as its gauge equivalence classes. Could it possibly be that also the gauge equivalence classes of gravity are actually information equivalence classes? So that if you use two different coordinates, then after a while you cannot see anymore in which coordinate frame you started. And my answer to this is a resounding yes. This would explain a lot, because it would mean that we might have a preference coordinate frame. You know, I'm now shouting one blasphemy after the other to this audience. First I said quantum mechanics is not what you think it is, and now I'm saying general relativity is not what you think it is. General relativity is instead more badly broken than quantum mechanics. So we have, there is a preference coordinate frame, but for some reasons that will have to be explained and discovered and understood, it is if you use two different sets of coordinate frames to describe what's going on in this world, after a while you can no longer distinguish them. And you might evolve to a state where you cannot find anymore what the coordinate frame was in a distant past, where these particles actually were in a distant past. This generates a beautiful form of non-locality in the deterministic description of the underlying theory, a kind of non-locality that maybe explains why we are thinking that particles become entangled. So I have a number of arguments to to mention in favor of this. One is the near flatness of the universe. How can it be that the universe is nearly flat? If the universe were based on laws where curvature is elementary, why should the universe be so flat as it is? Well, my answer is because there is some classical preference for a rectangular coordinate frame. So maybe there is a rectangular coordinate frame, and there will be oscillations between one choice and another choice of coordinates, but on the long run, the universe is actually flat. So, so the strange thing that you have a vanishing cosmological constant could possibly be related to this. Again, I'm not saying I'm solving things, I'm just putting things in a perspective that makes it easier to think about all these problems. Then you get the uncertainty of the position of a particle. The position of a particle has to be mentioned in terms of a coordinate frame that we don't know. So we actually, for every particle we talk about in the universe, we don't know where it is in terms of the rectangular coordinate frame because we don't know the coordinate frame. And this could be the source of a strange kind of uncertainty in the positions of particles, which may be precisely the kind of uncertainty we need to understand entanglement of particles. So, and then the induced metric of the system, G mu now is a derived quantity, will be fundamentally non-locally correlated. And there's another intuitive reason for introducing information loss. Information loss may enter in a big way in physics. In fact, when you do computational science, you find that time non-reversible programs in a computer are much more interesting physically than time reversible ones. Time reversible ones usually only give white noise because every state has a past, so why not you get the situation after a while that every state has the same probability? No, in nature, different states have different probabilities. There are thermal fluctuations where low energy things are much more probable than high energy things. How can it be? And that's again the intuition of a computation scientist who say, well, that's because some states are more probable than others because they have a larger set in their equivalence class than other states. And so to have information loss helps to give structure. It also helps us to understand the vacuum state. The vacuum state is not vacuum in this picture, it's full of vacuum fluctuations. But the vacuum fluctuations are now real fluctuations of ontological things, but the vacuum state is probably the most probable state that nature can be in. So now we can define energy in terms of probability. The most probable state is the lowest energy state, and the less probable states will be higher energy states. So this gives much more structure to the underlying theory, structure of the kind that eventually we'll need. Now, when you talk about quantum gravity, you have to talk about black holes, and so lots of my arguments now I plan to talk about black holes, but I have not so much time, so I'll summarize what was found about quantizing black holes. And now black holes, when they are large, they're very rare and esoteric things, and many theoreticians consider black holes are just an oddity in their theory that you rather not think about too much. In string theory, black holes are very odd configurations of strings and branes and so on, but to my mind, black holes must be much more fundamental in the theory of quantum gravity. In particular, virtual black holes. It should be possible to have black holes in the vacuum fluctuations. Vacuum fluctuations, as you know, in a standard model, the vacuum can, in principle, fluctuate into anything. With very low probabilities, but it can fluctuate into anything. So the vacuum could fluctuate into black holes all the time and get out of this black hole as easily as it got in. Black holes, as you know, they radiate particles, so you can get out as easily as you can go in. And this will be in the vacuum fluctuations all the time. So if your theory of black holes would violate quantum mechanics, then your whole standard model that you construct out of it would violate quantum mechanics in a big way. That we don't want. So I'll just quickly summarize now then what was found about black holes, which is different from what people usually think. And my theory does contain assumptions, but I only make assumptions which are very compelling to my mind. String theory is not a very compelling assumption, but the assumption of string theory are basically big steps, that particles are strings. I'm not ready to accept that yet. Maybe that's because of my limited understanding. I don't understand string theory well enough to have a good intuition in that field. So I say for a moment, let's leave out the strings. This is now a pre-string theory, because strings might enter later, but I want to see them enter, and then I will welcome them. But I'll first try to understand black holes without string theory. And there's a lot that you can do. So, so the new findings that I wanted to talk about more, but maybe then in breaks and so on, and you can look up in various publications. The new findings are that in our so-called pre-string theory, that ingoing particles and outgoing particles of a black hole are actually related. In more conventional theories of black holes, whatever you throw into the black hole does not have a direct effect on what comes out. That, according to what I actually found, is not true. Ingoing particles do affect the outgoing particles gravitationally in a very bad and a very fundamental way. They leave a footprint in all the outgoing particles. So any ingoing particle has its footprint left in the outgoing particles, and vice versa if you go backwards in time. Since I'm giving a quantum description of black holes, I now again want a time reversible prediction. So the states I'm looking at, in the back of my mind, they are elements of equivalence classes. But I leave that aside for a moment and try to understand first quantum black holes as well as possible. So the elementary states, the black hole can be phrased, can be used to phrase the black hole, are the momentum states of the ingoing particles. So I have to define the momentum distribution of the ingoing particles, and that fixes the momentum distribution of the outgoing particles in a beautiful way that you can calculate. Practically no assumptions went in, besides the fact that at the classical limit, ordinary generativity should hold. And then you can compute how the momentum of ingoing particles determines the momentum of outgoing particles, at least in a quantum mechanical sense. And then the big discovery is that these equations are linear in the momentum. And that means that you can describe everything in terms of spherical harmonics. So a black hole, let's assume the black hole to be symmetric. What is that statement? I can't read, I'm sorry. 10 minutes, oh, thank you very much. Then, what was I saying? You can, everything was linear, and so you can use the spherical harmonics to describe the ingoing states. You'll find that the outgoing states, or the footprints, they are diagonal in terms of L and M, the angular momentum quantum numbers of the spherical harmonics. So you can look at the footprints of ingoing particles that the ingoing particles leave on outgoing particles by going into the spherical harmonics description and say that for every L and M we have a separate equation, and different L's and M's do not directly interact. So a particle in a spherical component of the spherical waves only leaves its footprints in the same spherical wave components of the outgoing particles. The nice thing about that is that the differential equations you get this way are one-dimensional differential equations, very easy to solve, and so you can actually now compute the scattering matrix by which a black hole sends ingoing particles back into outgoing particles. And this is marvelous, because now you can learn a lot from this. You can read off that this matrix is unitary. We didn't have that before. People assumed that the matrix had to be unitary, but now you can read off. And you can read off the price you have to pay for this unitarity. It doesn't come by itself. No. What you find is that if you know what the Penrose diagram is, it describes the different regions of space and time near the horizon of a black hole. You find there are two regions near the horizon of a black hole, and these two regions are entangled. They are entangled so much that it's somewhat difficult to separate them. Many people think that black holes are gateways to other black holes via the so-called Einstein-Rosen bridge. That, unfortunately, cannot be true. And the reason is this entanglement, that this entanglement would imply immediately that operators on one black hole would not commute with operators on another black hole. That simple calculation you can do, that the operators on different black holes don't commute. If they don't commute, you cannot have that one black hole allows tunneling into another black hole if they are space-like separated. But the tunneling effect should depend on how black holes are separated. So having signals having one black hole directly connected via an Einstein-Rosen bridge to another black hole gives you direct contradictions with locality. It can't be. The obvious solution there is beautiful, which is that you have to say that the two regions of the pendulum diagram connect antipolar points of the same black hole. Now, I haven't seen that discussed a lot. It was discussed a lot long before I got interested in the subject by Sanchez and Whiting. So I'm not the first to say that different regions of the black holes could actually be connected through their own wormhole, but it works. If you assume that the theory will be unitary, the black hole will be in a very entangled mess, but only with itself. One side of the black hole will be entangled with the other side of the black hole. That's not in contradiction with anything. If you look very carefully, it's also not in contradiction with locality, with commutation rules, and so on. So this part of the theory works beautifully. A number of other observations. I can't take the LM values of the spherical harmonics too high. L should not be bigger than the mass of the black hole in Planck units. So if the mass is 100,000 Planck units, then the maximum value of L is 100,000, not more. So, but in general, for every L and M, you have a simple 1 plus 1 dimensional differential equations that any graduate student, even undergraduates, can solve. So, yes, and Hawking particles will be entangled due to this. So that's a very interesting feature of this theory, that Hawking particles on one side of the black hole are entangled with Hawking particles coming out of the other side of the black hole. That's not what Hawking would have predicted. So we see a modification of Hawking's computation of Hawking particles in a very interesting way. There is a new kind of entanglement. And the other thing is that baryon number cannot be conserved. This we knew about black holes, of course. They can absorb much more baryons than they can ever emit during their lifetime. So baryon number cannot be conserved. And that gives very interesting constraints on the kind of standard model you want to use to describe sub-Planckian particles in the vicinity of black holes. Those standard models, whatever they are, cannot conserve global quantum numbers such as baryon number. There are no firewalls, but again, it's easier said than done. Many investigators find that there's a firewall in a black hole. In this theory, you can remove the firewalls by fundamental transformations. Those transformations are not obvious when you start looking at black holes, but there are transformations that leave their properties invariant. You have to use such transformations to remove the firewalls, and this way you get a completely consistent picture of all microstates of the black hole. So the theory then remains time reversal symmetric, but formally, if you could go faster than light, you could go through the horizon of a black hole and re-emerge at the other side, PCT inverted. You change into an antiparticle, you go backwards in time, and your parity is being flipped. A very strange kind of experience you should undergo. Of course, nobody can go faster than light, so because of this, you get something else that comes out of the black hole at the other side if you go in. This is all described in the theory, and it all works. It makes the black hole unitary again. So. I have here a remark about central charges, because the algebra I find is very similar to the algebra of string theory. So I said before, this is a pre-string theory, perhaps not for very long. Maybe string theory comes in, because I find the same Virasoro algebra to be applicable here in principle, but I haven't understood it. In particular, I have not understood the elements of the Lorentz transformation, which moves you out of the horizon. For string theory, that exactly would be the source of central charges in your algebra. So I have no central charges. That's because I'm not such a good physicist. If I were better, I would find those central charges at a later stage. But most importantly, space and time become non-trivial this way. And the most important thing, it was on the previous page, that the black hole has no interior. And this is a new feature of the theory. If you want to have pure quantum states, you should remove the interior of the black hole altogether. So the black hole is not just black, it's a black hole whose interior is not even space-time. There's nothing there. In fact, the points on one side of the horizon must be linked to a point at the other side of the black hole. So these 2 points, these 2 axes and the line in between are just a single point of space-time. And the same thing here with this circle and that circle are the same point in space-time. This double circle and that double circle are also the same point in space-time. So the interior is simply nothing. In this picture, blue is space-time, white is not space-time. It is not even vacuum. I call this a vacuole, with some resemblance in biology. And actually, a virtual black hole, or even a black hole that has a beginning and an end, is a vacuole in 4-dimensional space. You also have negative time linked to positive time if you go through this vacuole. In a way that makes the whole picture remarkably consistent. At first sight, you'd say, this is nonsense. If you invert time, you are inviting all sorts of crazy ghosts in the theory, but not here. The crazy ghost just goes out because you identify time this way. Now, my last chapter is about virtual black holes. And virtual black holes then also modify space and time this way. There are little vacuoles in space-time which fluctuate. They fluctuate on and off in a way that will be classically difficult to understand, except when they are fundamental elements of the classical theory. So linking this to what I said previously about quantum mechanics is going to be very difficult and has not been done. But in principle, I would invite anybody with some imagination to see how you can turn this into a classical theory. So I consider vacuum fluctuations classical fluctuations. Now, a black hole would be, again, such a vacuole, but now when we have virtual black holes, of course, we have vacuoles everywhere. And these white circles, white three spheres actually are, 3 spheres embedded in 4-dimensional space-time, they force us to identify antipodal points. That makes space-time very non-trivial. In fact, it gives rise to space-time foam in a way. This is what previously was called foam. In fact, it becomes much more foamy if you look at more virtual fluctuations. It is a property of space-time that no matter how small the region is, there can be little virtual black holes in it. And these virtual black holes cause regions of the space-time to be excavated. So all of space-time is being excavated. And you see, if you continue this way, that the only thing that survives are these membranes, so to speak, the horizons themselves, which are 2-dimensional surfaces. I'm sure that string theorists will like that picture, that actually the underlying theories will be rather 2-dimensional than 4-dimensional. These fundamental surfaces that survive in this picture are basically 2-dimensional surfaces. So now you see that space-time is being changed in a big way if you try to quantize black holes. So I think the ultimate theory of space-time is a theory which has space-time in this particular shape, fluctuating all over the place, being topologically non-trivial, and now it will be our task to figure out what the equations are. This is as yet way beyond me. So yes, I have to end the talk with many question marks. But I do end this talk and invite you to read more about the theory and its interpretations, both the stories about black holes and the story about interpretation of quantum mechanics. At first sight, they seem to be very different subjects, but I think personally that these subjects are very strongly related. And Chairman tells me to stop, so I stop. Thank you. Thank you.
I have a question about your cellular automaton theory. Normally, we can think of classical mechanics as a limit of quantum mechanics where let's say the energy spacing becomes very small. Can we think of quantum mechanics as some limit of your cellular automaton theory?
No, quantum mechanics is not a limit of a cellular automaton theory. It is the cellular automaton theory. So the thing is that a cellular automaton has, as you know, all these little computer memories arranged in a lattice, and they evolve according to some classical evolution law. I attach to that classical evolution law a unitary operator. And that unitary operator is then exponentiated in terms of a Hamiltonian. That is the Hamiltonian of a Schrödinger equation. I don't have to consider any limit. It's very important to emphasize this.
Thank you.
Yeah, could you please give a good understanding of the collapse of the wave function? What is the mechanism of a collapse of a wave function?
A very important question. I forgot to mention, because of time limits, that the universe is in a quantum wave. There is a quantum wave function of the universe. This is a difficult subject for many people. They think that the wave function changes if you do a measurement. Not so. The act of a measurement is just a physicist switching on a machine of some sort. All that is part of the same unitary operator of the universe. Nothing changes. If you look carefully, what does it mean for the wave function of the universe? You find the wave function doesn't change when any measurement is made. It was in the collapsed state all along. The ontological wave function of the universe only contains delta peaks or ones and zeros, and nothing in between. So the universe is always in a pure single quantum state. So it's only ones and zeros. One is what's true and zero is what's not true. It always is like that and stays like that. When you do a measurement, you are figuring out what the probability was, that this is the outcome and not that is the outcome, but that fixes the probability of the initial state. But the universe always was in that initial state from the beginning. So from the Big Bang on, the universe is in the state that is collapsed, and it always stays in there. When we do a calculation, we use quantum superpositions, not because nature is in a superimposed state, but because we don't know nature's true state. We don't know the initial state. That's why we use wave functions. But as soon as we measure something, we will learn something about the initial state. And so in that respect then, the collapse of the wave function is just like the collapse of probability distributions in a classical theory. As soon as you measure something in a classical theory, previously you didn't know the initial state, and you had a whole set of possible initial states. As soon as you do a measurement, you learn something about the initial state. Your probability distribution collapses. Of course, physically speaking, nothing changes, but only your understanding changes. So in my picture of quantum mechanics, exactly the same thing happens. So the wave function going into a delta peak is only because now we know better in which state the universe actually is. So no physical collapse takes place.
Thank you.
Does the granularity, which is so evident in your pictures and in the notion of cogwheel, mean that we should expect space-time to break down on some small scale, detectable, for example, by violations of local Lorentz invariance? And what scale would that be?
Well, Lorentz invariance and other symmetries are very difficult to understand this way. And I think you might call that a weak point of my theory, which is where do all these symmetries come from? And particularly, they have continuous symmetries. So you're quite right. Lorentz transformations form a continuous symmetry group. Very difficult to understand this way. What I can say about that right now is Lorentz symmetry is not a good symmetry of the universe, because the universe is definitely in a particular state with a particular velocity. Right? So the universe as a whole is of course not Lorentz invariant. The local laws seem to be. So it is an important assignment, and I realize this very well. I should understand where Lorentz invariance comes from. And this is a mystery that may have to do with this transition from coordinate frames to other coordinate frames, and which become invisible to us. So we even don't know how our coordinate frame is rotated. So because we don't know that, our wave functions contain all rotated versions of coordinates. And that induces a symmetry in our description of nature, but not in nature itself. So this is the kind of granularity I would expect. It might go on much further than this picture, that actually you have just discretized points. But when you look at my way of handling black holes, Lorentz invariance is built in. So as soon as I use quantum mechanics to derive things, of course I use Lorentz invariance. So maybe it's fair to say that my answer to your question is a long answer, because I don't have the complete answer at hand. I can only guess what the answer might possibly be.
It was a long answer, but I understand where you are much better. Thank you.
Thank you.
Is there any place for the Wheeler-DeWitt equation in your scheme? What role does it play for your wave function?
In the sense that the Wheeler-DeWitt equation is a Schrödinger equation with very complicated variables. I have explained, I hope, where Schrödinger's equation comes from. It comes from a classic equation where you have replaced the evolution operator u by its exponent h, and the Wheeler-DeWitt equation, of course, does the same thing. So ultimately, of course, whatever you could call Wheeler-DeWitt equation would be replaced by a deterministic equation in this picture, and then if you, again, you have no fundamental knowledge about the initial state, you are forced to use probabilities, and if you use that, you may well get something like the Wheeler-DeWitt equation out. After all, the Wheeler-DeWitt equation is nothing but the statement that I attached elements of Hilbert space to the state a general relativistic system can be in.
Thank you. One more question?
You know, there's this beauty factory in Japan, and there are these B mesons being produced all the time. And for example, it has one of these B mesons, it has more than 100 decay channels, you know, with small branching ratios, 10 to the minus 4, 10 to the minus 3, or something like that. So are you saying that actually the creation created these? They knew from the beginning, so we did not have just one B meson, but we had, let's say, more than 100 B mesons with the same mass. They knew they were going to, how they were going to decay.
I have to emphasize, thank you for the question, I have to emphasize that predeterminism or superdeterminism, I should say superdeterminism is not the same thing as predeterminism. Predeterminism is that some entity knew in advance what was going to happen. But if you suspect or assume, like I do, that nature is a gigantic calculating machine, the calculating machine itself doesn't know in advance what will come out of its calculations. We just have to wait and see. So nature, in my view, is the fastest calculator that exists, and nothing in nature. You cannot make a computer in nature that calculates faster than nature itself. That would be a contradiction. So it means that nothing is predetermined. It's not true that the way all the beauty particles decay is somehow written in the books before they actually do the decay. And that's because the equations are so complicated that the fastest entity that can compute how things decay is nature itself. So when the decay takes place, it's the first time that nature lets us know how these particles decay. There is no faster way. Nothing is predetermined. But superdeterminism means that yes, the initial state determines in a way which is way beyond our ability to calculate, but it is determined by the state that nature started off with. So yes, all these B particles decay according to some definite law. There is a question about particle decay, by the way, and that's how come that we get an exponential decay law. But that comes about because of vacuum fluctuations. The idea that the vacuum is not a single state. In our description in quantum mechanics, we have a single state we call vacuum. But in the ontological theory, the vacuum contains huge numbers of vacuum fluctuations, which never repeat themselves completely. They are different everywhere. And that's why any B particle lives for a different amount of time until some crazy fluctuation hits it from the outside of the vacuum fluctuations, make it decay.
Okay.
So,
you know something? Since I consider you to be a friend, I'll tell you something, but don't tell anybody, okay?
I'll tell nobody. You kept completely secret in this hall. Yes.
I'm allergic to time reversal. When I hear time reversal, I start shivering like mad because nobody, not even a magician, has ever reversed time. So it's never a question of time reversal. It's always a question of motion reversal. And since for you, the initial states are extremely important, and I think that you should not be allowed to talk about time reversal, because in initial state and final state they change roles, and then somehow the whole thing becomes much more complicated. That's my opinion, but don't tell anybody.
But I won't tell anybody. But actually, if you say this, you could say much more. There's
I could say, but I didn't.
There's also the operation that if you interchange 2 electrons, you get the minus sign. Have you ever tried to interchange 2 electrons? It's equally difficult. Equally impossible.
But that's, but we always square all the amplitude and things like that. Okay, I mean, that's just a theoretical, mathematical description.
So it's true what you say. It's not that nature can be inverted in time. It's the mathematical description of nature. We can compare the mathematical equations going forward in time with what the equations would say if you look at how things go backwards in time. And the statement, the usual statement of CPT invariance is that yes, you can compare the equations forward in time, you can substitute the time parameter by minus the time parameter and discover that system obeys the same equations. That's really what time reversal is about. So I don't think you would have any difficulties with that. It's not that we can actually invert time, but we can invert time in our equations. So that means that time reverse invariance only makes sense once you have a model of nature, once you have equations. Then in those equations, it's very easy to change time. Just put a minus sign everywhere in that equation and see what happens.
Gerard?
Yes, David.
Do I understand that if I were to fall into a massive black hole, when my head hits the horizon, it would appear instantaneously on the other side of the horizon?
Unfortunately not, because you can't go faster than the local speed of light.
So what would happen?
Since you are going, since you're following your proper time, you are too late. You come out of the black hole after eternity has passed. That's no good. We won't be able to see you come out at all.
There's no inside.
Actually, what comes out is your footprint.
There's no inside.
There is no inside, so you go into the inside, but actually what there is a region 3 in the Penrose diagram, which is a region out of which you can never escape. You can only be killed by the singularity.
So,
but what you do leave...
There's no inside.
Sorry, there's no inside. But what you do, there is a footprint. You leave a footprint behind in all particles that come out. And so if I look at all parts come out and I take that tremendously complicated wave function, I Fourier transform it, I still find David Gross written in that.
As far as I'm concerned, how do I distinguish that from a firewall?
No, that is no firewall. Those are soft particles.
No, me.
You. How should I say? The particles come out are all Hawking particles. They all go much, much slower than...
I'm asking about what the observer falling into the black hole observes.
It is in the description. You can... your footprint is in soft particles. Particles
from the outside.
From the outside. So the outside world to say, we don't see any firewall.
But can you describe what I would see? What I would measure?
You would, well, you like to survive your journey through the horizon. So the only proper description of that is to first remove the firewall by a transformation, like a gauge transformation. In which gauge do you come out? You would ask me. Well, you can say, well, I can transform to any gauge. Of course. So I transform the equation such that you see no firewall, and then I can describe how you proceed in the region 3. Not very useful for physics because we can't see you coming out. So whatever I describe in region 3 is actually immaterial. So for you it's perhaps important, but for the outside world it isn't.
No, I'm not questioning importance. I just know, how would I describe being in
the description is
space that doesn't exist?
The prescription is not unique, and neither does that matter for a quantum theory of black holes, because what's unique is what the outside observer will see. That's unique. What you will see, we don't care.
Well, Gerard, okay, don't care, but the question is very simple. will I be killed or I will not be killed when I go through the horizon?
Yeah, but it's
I am not interested in description, yeah? I am flying, I am sinking. And the question is, okay, will I be killed or I will not be killed? Or I can check that you are right or you are wrong.
No, but you can't tell me anymore because you are in the wrong place. You're not in a position to tell me.
I don't care about telling you. I am interested about checking your idea myself, you see? Okay, question is, will I be killed by firewall? I will be killed.
You can kill my theory after eternity has passed. So, and you're quite welcome to, I don't care. I won't survive to see that happen.
I think we run out of time, so you want to make some announcement. Thank you again for our speaker.